Okay, hello, welcome back to another one of my video log recording sessions where I talk about genetic algorithms. Okay. The date is 2025 June 18th and the time is 2:35 a.m. and it's been like 4 to 5 days maybe since the last video. To be honest, I haven't really done much after that because well, turns out after having almost completed or just completed the dynamic genetic algorithm part, I'm lost again. I don't know what to do next. Like, actually I do know. I have to move on to chaotic genetic algorithm, but that I'll talk about that later, but that would require me to learn some new concepts, new stuff, so I'm also looking into that, but in the meantime I felt that I need to, well, once again go over what I've done so far for the last few months. How long has it been? It's been like more than 4 months, I think. So yeah, probably around 6 months. So yeah, I think I've done a lot from the very basic stuff and onto some complex stuff, but I really have no clear idea if what I've been doing for the last 2 weeks is or can be classified as, intermediate, at least. So to get a grasp of what I have been doing and what I'll need to do, today's vlog session will be me trying to go through everything. So here we go. Well, this is the spreadsheet that has almost all the Jupyter notebooks and the titles of the videos that I've done so far. And this didn't really help. Well, it does help, but it's hard for me to draw a mental map in my head. So I did that on some paper, some pieces of paper, or A4 paper, and took pictures. So I thought this would give me some sort of a head start, or like a general skeleton, or could serve as a backbone of what I want to talk about for today. So let's have a look. I hope we can actually see this on video. But well, here we go. So I started. Let me just before I actually start, let me just get a good look. Record the entire thing on video. There's that part. There's that part. It goes this way. Oops. It goes this way. This is 1, 2, 3, 4. So there's a second part, page, third page, and the last page. Chaotic dynamic. So onto the first page. I remember having started off with vanilla, or I didn't actually name it vanilla genetic algorithm back then, but it was called, it was just plain and simple basic genetic algorithm with 20 items. And I remember that the very vanilla, the very basic ones kept giving me a summed utility score of 6. I started with 660, and then it was 670, and then I started getting 690s, and then I suddenly started getting 700 and 705, and then finally 710, which actually is the true ceiling given these conditions, given these circumstances. Now, true ceiling, once again, I have to clarify, or, well, I have to emphasize that I don't know if this is the right terminology, but I named it so. Anyway, the true ceiling is, what is it? The best possible combination of, could be combinations of items or genes, since it's called genetic algorithms. Best now when it says combinations, this means chromosomes. So that's what the true ceiling is. That's what it means. And with 20 items, with preset items. Now, preset is just the items and their utility values and the constraint values that I have actually sat down and just arbitrarily set, hence the word preset, as opposed to generated values. I know that preset values are also generated, because the difference is that the preset values are generated by me manually, but the difference there, the real difference there, is that generated values are generated by code, given some specific or random distributions. So this is with preset values. 20. I started off with 20 items, I think, and then I also wanted to actually try the brute force approach to actually check and validate my answers back then, because I was getting back then I was getting somewhere around 690, 685, and sometimes 700. So I wanted to, and maybe in rare occasions 710. So I wanted to check what the actual best possible answer was. It was 710, and during the early stages I got the 710 through brute forcing it. So this was validated as the true ceiling. And then I moved on to doing the first ever grid search. But in retrospect, I must say that when I was doing this grid search, I wasn't really clear on what I was trying to do or what I was trying to achieve. Even now, I don't really know what I'm trying to achieve, but back then, when I was doing this, I was even less clear, or less, less clear. But anyway, so I tested a lot I ran a lot of iterations of evolution by or with different numbers of generations, as in total generation or max generation. No, I should say total, because the word max may because the word max actually may imply that there would be some iterations where everything ends before it hits the maximum generation. But no, let's just say it's closer to the concept of total rather than max. So I tested, I did a lot of iterations, I performed a lot of iterations with varying total generations, with varying population sizes, and many others, but again, I didn't know what I was doing and with what parameters or hyperparameters that I should be testing with. So that was that. And then I made new or different procreate functions, of which there were 10 procreate functions. And then I increased the number of items to 30, and then did the whole thing again, and then I increased it to 40, and then 50, and then I even tried the same procedures with a lower mutation rate, because at first it was I think 0.03. I also tried it with the higher mutation rate, that is 0.05. But here, when I said I tried it with lower, I mean, it was probably 1 or 2. So 1% or 2%. So let's just put it like 0.01 to 0.05, I think. So, and then more generations. The default was like I believe it was 500, but sometimes also 300. I wanted to try for more generations for a longer period of time, so I would give it 1000 or even 3000. That's what I did. And then bigger population is when I tried, and I remember initially having started with 100 entities, and then maybe 500, and then I tried with 1000, and then at most I think it was up to 2000 or 3000. Yeah, I did that in order to see if I could, on a consistent basis, keep getting what I thought was the true ceiling for 20 items, 30 items, 40 items, or 50 items. And then I discovered that I was doing something wrong. I was doing something not entirely wrong, but in somewhat of a confusing way, and that was assessing the results of the evolution over a certain number of generations. Total generations, the generations in general. So anyway, I was doing it not entirely in the correct way, at least not the way I saw as correct, because I remember that I was like, when, if, for example, if this is the world and there would be 1,000, let's just say 100 entities, I was measuring the well, let's also have, like, if this is the world, and if today this is going to be the head, this is going to be the tail entity, and then I was only, well, at first, initially I was measuring the sum utility values of the head entity, and I think maybe the tail entity as well, and then the top, for example, 10% or 15%, the percentage, the number, this number doesn't really matter for now, and then the top 50%. But the way I did this is that first I would have these I would have all the entities, and I would calculate, let me just cough. Okay, I'm back. I think I'm okay. So, the way I initially did it is that when I compute the sum utility values of the entities, I would not take into account how many entities scored or had such a had a specific sum utility value. All I did was collect them in a dictionary called entity dictionary, and then have the sum utility value as the key, and then have the entities in that dictionary as value. But I don't know, maybe a list of entities like that. But the way I did it is that if it was for the head entity, I would just refer to this, and then that would be it. But for when calculating the top 10%, for example, if this is K1 and this is K2 and then this is K3, I would only I would try to get the top 10% of the keys. So if there were for given 1,000 entities, if there were 600 keys, I'd get the average of 60 keys. 60 keys. And not accounting for the weights and how many entities there were given that key, per key. So I would ignore all of that and then just get the average of top 60 keys, which I think is wrong, because naturally, some entities would have the same, whether they're the same or not. Some entities would have the same summed utility score. So the average of top 10%, for example, should be somewhere up to here, maybe until the 30th key, for example. So the metrics that I was gathering had a tendency to, in many cases, underestimate the actual performance or the actual results. Underestimate the actual metrics. So I had to change that, and so the way I changed it is that for the head entity and the tail entity, it stays the same, because I'm just measuring one entity on each end. But for the top 10%, if there were 1,000, maybe in one case, within one generation, if there were 900 entities, I would calculate the sum of 990 entities, because 900 times 10%, which is 0.1, is 90. So what I would do is I would sum up the summed utility scores of the top 90 entities, and then divide that by 90, and that would be the score for the top 10%. Same for 50%. Get everything until the 450th entity, sum it up, divide it by 450. So that's what I mean by this bit, new way of assessing. Let's see, dictionary key based to actual top summed utility values, sum of actual top summed utility values. And then when I did that, after having done that with the new method or new concept of these metrics, I went through the entire thing again. 20 items, 30 items, 30 items, 40, 50 items, test the 10 procreate functions, like here, test the procreate functions, the test combinations of procreate functions. But to be honest, this bit, combination of procreate functions, actually led to nothing. It was hard to back then it was difficult to determine when I should change the procreate function within the iteration, within one run. Do I keep the first procreate function until generation 200 and then switch it to another procreate function after generation 200, etc., etc., and after having used the second procreate function, do I change to another one or switch back? So it was tricky. That one was tricky. So I just moved on. I just moved on to this bit: max constraints, max constraint percentages, and dips and plateaus. Now, the reason I kept on trying, even after, or especially after getting the new metrics, the reason is that I kept on getting dips and plateaus and peaks. Now, what is a dip? When you have this plot, this is the summed utility value, and this is the x-axis is the generation. And then when you have a plot, what used to happen is that when dealing with more than 20 items, like 30 or 40 items, they all had a tendency to just peak and then fall back down. So this bit was the peak, and after that, this flat part was the plateau, and then the difference in level, this is what I called the dip. And that was also the reason why I kept on trying all the other procreate functions and combinations of procreate functions, because first it was frustrating to see that entities would reach so high in terms of some utility values while not going over the max constraint, but after some number of generations, they would start falling down, decrease. There would be that decline, and then they would just plateau right here. It's frustrating, and from the entities, from the perspective of the entities, that's sad. So I wanted to fix that. I wanted to, straighten out that issue. Why does the dip happen? Has it got anything to do with max constraints or max constraint percentages? I didn't know, so I had to check that out. So we go on to that question: why do dips happen? Now, if I say a dip happened, it usually meant that there would be the peak, and then there would be the plateau. Something like this. And when they would actually peak and then plateau, would sometimes be quite different, but they used to happen nonetheless. But why? Did it have anything to do with the distributions of values related to the items, as in for the utility values and the constraint values? Like, does it have anything to do with how their distributions look like? Or has it got to do with the maximum constraint, or the maximum constraint percentages? Now, what is a maximum constraint percentage, you might ask? So, the sum, where we go? The sum, there is something that I call the total constraint, and that is the sum of all constraints of items. So if there were 100 items, the sum of the constraints of all those items would be the total constraint. If there were 1,000 items, then the sum of all 1,000 items in terms of constraint values, constraints. And the maximum constraint percentage is which color should I use this? The max constraint percentage is maximum constraint divided by total constraint. So that's it. So I was wondering if this or this had anything to do, if they had anything to do with the dips. Spoiler alert, not really, no. So that's what I mean by this part: peak, plateau, and dip. And when I was, in order to also verify if they had if the occurrence of dips had anything to do with distributions of values related to the items, I had to generate I had to write the code to generate the values for these items per iteration. So they were not preset anymore, and that's what the term general meant. That's what I meant by general, this bit. And then for the types of distributions that I used, there were normal distribution, normally distributed. The values, either the constraint values or the utility values could be normally distributed. There were 8 of them, and let's see if I remember all of them. There were normal, there were uniform, they could be uniform, they could be log normal. No, oops. Oh my god, I keep doing that. I feel so bad. Let's see, normal, log normal, uniform, what was it? Uniform. Wow, I forgot. Okay. Let me just see. There were 8 of them. I remember the last one. It was left skewed. Left skewed. And then there was, I think, variable. And then Pareto. I need 2 more. There was, no, was that right skewed? Oh yeah, exponential, which is kind of similar to log normal, the way I did that. Log normal, Pareto. Just one more. What was it? Seriously? Okay, I give up. Von Mises. Oh god. Von Mises. Was it Von Mises or Von Mises? I don't really know. But anyway, those 8. And then while I did that, I made these plots that I ended up calling peak plateau plots, the PP plot, and where the x-axis would be the maximum constraint percentage, and the y-axis would be the, well, summed utility values. And usually there would be 2 lines. The upper line would be for the top would be the summed utility values of the heads of the head entities per, or head summed utility values of the heads per maximum constraint percentage, and on the very end, the last maximum constraint percentage would be this bit would be 100%, or just 1.0, and the first would be like something like 0.1, and then there would be another line right below that, which is the, or something like this, which is the average of top 10% entities in terms of summed utility values. So that's what the peak plateau plot portrayed. And then for these 8 distributions, which were used to generate the utility values and the constraint values, generate or sample, whatever, sample these 2 sets of values but separately from these 8 types of distributions that I defined, and I had to make sure that they were sampled separately while not using any kind of a random seed, because I wanted them to be different, even if they were from the same distribution. So there would be 64 distribution products, 64 types. For example, the utility value could be from normal and the constraint value could be from normal. That's one. The next iteration could be utility value normal, constraint value from low normal. The last one, or the second last one, would be something like the utility value could be from the left skewed, the constraint value could be from variable. Yeah, so variable or variable. So there are 64 of them because there are 8. So 8 times 8 is 64. So that's what this means, 64 distribution products. And I tried again with some arbitrary values for 10 with 10 items, which was quite quick to compute for the run to finish, for the iteration to finish, and then with 40 items, and then with 100 items. I do remember having spent somewhere close $130 because I wanted to try doing this on Google Colab, and then because I knew that these two parts would take a lot of time, so I used the paid version of Google Colab, and it cost me $130, which was not worth it, by the way. So that was sad, because the way I coded everything does not utilize GPU, so I couldn't actually get my money's worth. So then I moved on, and then I realized that I was doing something wrong, because it wasn't a matter of the dips weren't a matter of which procreate function I was using, or it wasn't actually a matter of what the max constraint is or what the max constraint percentage is, and it was not a matter of what the dips, I mean, as far as the dips and the plateaus and the peaks were concerned, it was not a matter of what distributions the utility values and the constraint values were from. The dips were happening because I was putting the newborn entities at the end of the world within each generation. So there would be the existing entities, and then that would be the newly generated, the newborn entities. And then the way I was doing it was that initially I was just putting the newborns at the back, and then I was using the selector function first, and then I used the limit population function after that. So on quite a regular basis, the newborns would be cut off. They would not survive onto the next generation. Onto the next generation. So there was a limit to how much the newborns could contribute to the overall performance, to the overall wellness of these entities. So what I did after having found this out, was I did the opposite. Can I call it the opposite? I put the newborns at the front. Yeah, I put the newborns at the front. Oops. And then the selector function would do its job, and then the limit population limit function would do its job. And this way, mostly the entities with low sum utility scores would be limited out of the population. So that eliminated doing this eliminated all the dips from happening. That's what it used to be, but after this I kept getting that. So now there are no peaks, only a plateau, so no dips, because there's actually no peak and no plateau with a difference in level. There is no dip. That's what I kept getting. Yeah. So that's what I mean by this better evolution scheme. And this was just me putting the newborns at the front. And it says even without shuffling, because I did end up shuffling the entities before the population limit function was applied. Yeah, and this is when I remember that this is when I started putting the population size, when I started setting the population size same as the max population size. And I think I can start having a different. What did I actually just write max size, max population size? Until now these two values have stayed being the same, but I think I can have the max population size bigger now if I let the newborns from the procreate function, if I let all the newborns from the procreate functions survive, or yeah, if I let more newborns, newly born entities from the procreate function to survive. Yeah. Right now it's just 1.5, but yeah, I can try that later. So this is when more new entities get introduced. And then and then by doing this I would actually have the world size bigger than the maximum population size. And then because I also ended up shuffling it, some newborns would survive, some won't, but overall the population size, for example, could be 1000, and then the max population size could be 1.2 times more, which is 1200. 1.2 times that is 1200, and then yeah, and then I could just cut it off at the 1200 mark, or cut it off at the 1000 mark. So that's just, yeah, I can try that later. So that's done. And then general genetic algorithm, all distribution products with better evolution scheme. Yeah, and I did that, and then that's when I realized that with the new and better evolution scheme, the peak plateau plot would just look like that. Oops. Would just look like that. Oh, come on. Yeah. This is for the head entity. This is for the top 10%. And this is where the maximum constraint percentage is at 1.0 or 100%, and usually this is the total utility line. So this is the sum of utility values of all items, and naturally, if you think about it, if the max constraint percentage is at 100%, then the true ceiling would be the same as the total utility value, the sum of all utility values. So after having done that, which cost me more than $130, I went into let me just rephrase that. I decided that I wanted to look into the lifespans and their behaviors, lifespans and behaviors of entities themselves. Because so far, until this point, not here. Until this point, all of this was looking at things from a macro perspective, and it was all good and all, because now the issue with dips was resolved. The dips were not happening anymore. But what was actually happening to the entities? Seriously. So let's go look into that, I decided. So I moved on to individual entities, and to do this I needed a way to be able to track individual entities. And this is when I started doing only one iteration per testing. So far, up until before I wanted to start looking into individual entities, I would usually do 5 runs or 10 runs of the same thing, and all the entities would just be a list of items. Well, all the entities would just be the chromosomes themselves, just one list, one chromosome of themselves, and the entity would not actually have a name. Even if it was actually the same chromosome or entity, it would not be the same entity. It won't have a name, because that's how it was coded. So in order to start tracking individual entities, I started doing only one run, but while doing that, I made all the entities into a dictionary where data and information about one entity would be, well, stored. And it would have a key value. One of the key values would be chromosomes, plural chromosomes, and the value for this key would have a list of chromosomes, with the last chromosome being the latest chromosome, and the first list being the earliest chromosome that this one entity had, the starting chromosome that this entity had, and along with other features and keys that contained information about this entity. And then it says here, concept of learning. Concept of learn. What is this? Well, this is when I realized that as I plotted every summed utility plot for every entity, I saw that they were all spiraling down. Most of them were spiraling down. Too many of them. Because that's how it was designed. That's how I had designed it back then. So in short, the entities peaked. The entities on an individual basis peaked very early on, but within the first 3 generations. 3 generations maybe, or maybe at the most 5 or 10. That's still very short. They peaked quite early, and then all they could do from there is just go down in terms of some utility values. And I thought that was very, very sad and not ideal. If they are entities, and if what I'm doing is not just to come up with a solution for an optimization problem, I shouldn't do that. I should aim for some other way to ensure that the entities don't just fall off from the moment they are born. So that's what the concept of learn or learning is. For every entity, if an entity is given a chance to learn, it will refer to one of the entities within the top 10%, and given some rate of success per gene, per item or per gene, it would just imitate that entity from the top 10% or top 3% or whatever, from the top n%. And to do that, I had to where's my mouse? I had to come up with a way to select the entities that would get the chance to learn, which I call the learn candidates. How many of them, or what percentage of the world would be chosen as learn candidates, and etc. Yeah. And taking this one step further, I would set the first ever thing that I did on choosing the learn candidates is set ranges. It could be from, if for example, if the left part is the head now, as opposed to what I did like 20 minutes ago, and the right end is the tail, this would be the top 0%, this would be the top 100%, or the bottom 0%. But anyway, let's just put that as 1.0, and this would be 0.0. And what it means by range is that the learn candidate could be the top 10%, or it could be the first decile until the third decile. So this is actually 20% of the world. Or it could be from 0.3 to 0.7, for example. So that would be 40% of the world. Or it could just be the entire population within that generation, which can be denoted as 0.0 to 1.0. Or it could be something like from 0.2 to 0.8. So that would be 60% of the population, and on and on and on. So I tested all of that. I tested all of that, and there were 66 possible variations. And then with 10 different, is it 10? Yeah, with 10 different learn rates. Now the learn rate is the success rate that an entity enjoys or has in trying to copy each gene from one of the entities from the top entities, top something percent entities. So the learn rate could range from 0, as in they would still fail, to learn anything, or 1.0. They could just copy, basically. So that was 66 variations and 11 values for learn rates. Now it's called the learn rate because in machine learning and deep learning there is something called the learning rate. So I wanted to call it the learning rate, but that's confusing, so I named it learn rate. I know if I wanted to avoid it being confusing, maybe I could have just used the word mimic rate or success rate or something like that, but learn rate it is for now. And then another step after this, another thing that I did after this is come up with different ways to choose candidates and different ways to compute learn rate for each individual entity. And there were quite a few, but the best one has actually turned out to be the best learn rate method is proper tail, as in proportionate tail, where the learn rate just is like that. This is the tail entity, this is the head entity, and this would be 1.0, and the head entity would have 0.0. And the candidate method, when it comes candidacy method, it's either called the candidacy method or candidate method. But candidate method actually has less syllables, so I think I'll stick to that. Candidate method. The best candidate method, the one that works, gives a robust, gives the most robust set of results, maybe I should say, is the expo tail or exponential tail. This is where for every entity within that generation, the probability that an entity that entity is chosen as a learn candidate looks something like this. Oops, maybe I should use red. So for the tail entity, it would be all the way to 1.0. The second tail, or the second last, would be something like this. It would be slightly less, but significantly less, and it would look like an exponential distribution. So that's what I mean by that. Now the interesting thing here was that if I use the tail means it favors the tail. Proper tail, the tail here means that it also favors the tail. The interesting thing here was that if I use the exponential tail for the learn rate method, only the tail entity gets to enjoy a learn rate of 1.0, and the other entities would have a significantly fewer learn rates. So overall it yields worse results of learning from the top entities. So it's quite important to guarantee that the entities on the lower end have a somewhat proportional learn rate. Because for example the tail entity would have a learn rate of 1.0, but the way this works is that the second last entity would have a learn rate of 0.333, and then the third last one would have a learn rate of 0.2. You get the point. But if I use the proper tail method, the last one would have 0.1, and then the second last one would have a learn rate of 0.999, something like that. This third last one would have 998. The fourth last one would have 997, all the way to the head entity, where this learn rate right here would be 0.01 or something like that, very close to 0. It could just be 0 as well. But if for the candidate method, if I use the proper tail and then I choose, for example, 20% when using the proper tail method, what happens is that the entities towards the lower end almost always get chosen, because it's called, they're done by sampling, so and without replacement. So if the tail entity is always going to get chosen as a learn candidate. So after, when that is gone, the entity with the highest chance of being picked is the second last entity, because now it is actually the lowest ranking entity. So when it comes to choosing the learn candidates, it was somewhat more important to keep some level of randomness, while kind of ensuring that the last entity still got chosen and the second last one is still kind of likely to be chosen. But after a certain point, I had to make sure that all these entities here had somewhat about the same chance of being chosen. So that's why I use the expert tail for the candidate method and the proper tail for the learn rate method. And then after I did that, I moved on to dynamic genetic algorithm. Now, dynamic is when what I mean by the term dynamic genetic algorithm is that hyperparameters will now start changing. They can change. Now, the first ever, and there are approximately for now 8 different dynamic genetic algorithm settings. The first one ever, the most complex one being this one, where the number of items will change over time, starting from 10 items. And then on to 20, on to 30. Now, if you do that, I got some utility plot that looks like this, like a staircase. And then while doing that, I can also choose to set the population size to a fixed value, for example 1000, or I could have 100 entities when the number of items is 10. I could have 200 entities when it's at 20, and then after that 300 entities when the number of items is set to 30. And it turns out that doing this worked quite well. It takes around 55 to 60% of the time that it would have taken to do the same thing, while only the number of items would change, as in with a fixed population size. So this actually works, which was quite fascinating to see. And in the future, I think I'll keep doing that. For a smaller number of items, start with a smaller population size, and then have that gradually increase if the number of items increases as well. And then there were the other 7 settings. This is just one of the 8 settings. There were other 7 settings where the utility value could change per generation, where the constraint value could change per generation, where both of them could change, where only one of them would change, and then and then if you put the number of items here, so it's 2 possibilities per category. Yeah, per group or per parameter. So there were 8 of them, because 2 times 2 times 2 is 8. But the one with varying number of items proved to be the most complicated one, because I can actually do so much variations here. I could, for example, increase the number of items. I could also decrease it and then increase it back up. Yeah. But then, who's to say that these items are overlapping or not overlapping? The 20 items here could be not the same when I'm doing 20 items over here. So so I could be keeping all the 20 items as I increase the number of items. I could be keeping some parts of it, or I could just leave everything up to chance. But the conclusion was that given enough of a era, or now what is an era? An era is a number of generations. Or some number of generations with a specified set of values, or a specified value for the hyperparameters. Or simply put, an era is a number of a window, a time window, where the conditions are the same, where the environment for evolution stays the same, and then in the next era it could be different, and then in the next era it could still be the same, or it could be something totally different again. That's why it's called dynamic, because everything is subject to change. What was the point of doing all this? I really don't know. I just wanted to see if everything worked. And then, having done all this, I need to start chaotic genetic algorithm, and then chaotic dynamic genetic algorithm. Do I also need to do general genetic algorithm, GG algo, while doing everything dynamic? I don't think I need to do dynamic general genetic algorithm, because that'd just be doing the same thing over and over, because now I have proven quite a few times that they all behave in similar ways. But chaotic genetic algorithm is something that is very interesting to me. It just sounds very interesting. Now, what do I mean by chaotic? What I mean by chaotic is that because now everything kind of waits. Every entity, entities wait, or have waited so far, until that generation, until that big G is over, until each generation is over. They go through each phase of the evolution within that generation at the same time, or almost at the same time. There's always a phase, there's always a step that you have just taken and the next one that you will take. But chaotic is different. That's what I mean by chaotic. Now entities entities will be more individual, will behave more individual on an individual basis. They can procreate and then suddenly go through, suddenly be subject to the selector function. They can suddenly be left out of the, limited out of the population. Yeah, so they can be struck out or left out, limited out of the population. Maybe they get lucky, maybe they don't do that, I don't know. So the concept of a generation, or the concept of generations in plural, the concept of generation and generations, both singular and plural, will now mean less, because entities will be will behave very sporadically, very randomly. It might look random, but I don't know. But the biggest challenge here okay, I'm back. So, but the biggest challenge here is that I need to find a way to make things so that they act somewhat independently, somewhat individually, on an individual basis. It could be concurrent, it could be parallel, I don't know. I haven't figured it out yet. I think this is the most challenging part, maybe? Of course, where is it? This is the most challenging part. Incorporating all of this and then putting it into chaotic, dynamic, genetic algorithm. This is the most challenging part. Well, okay, I'll be well, let me rephrase that. These two would be the most challenging parts in terms of programming, in terms of well, my skill, because my Python skills. Or I might even have to start using another language, but I would really love to stick to Python if I can. Yep, and then that's about it for today. But I have to make another video, maybe right after this, or maybe tomorrow, which is on which will be on other ways to do or to solve the knapsack problem, which is what this entire thing is. The knapsack problem. That's what all of this is. But I know about the brute force way, but I found, and then there's the greedy way, and then there is the, again, dynamic programming way, the DP way. Now this dynamic is not to be confused with this dynamic, but anyway, that's what it's called, dynamic programming. And when you use the dynamic programming concept to this, when you apply it to the knapsack problem, that's called the 0-1 knapsack problem. But so I've tried that again. I think yesterday I did that, and yeah, I'll have to share my thoughts. Slight spoiler, this has its own merits. Very, very good, very efficient. But I'll try to find some reason or sets of reasons for me to continue on with the Jansing algorithm approach, trying to justify the time that I spent, or rather, that justification would come from weighing the pros and cons of each one of these methods. Yeah, that will be my next video. So thanks for watching. Let me just go record the whole thing again, the whole page. Yeah, I already saved it, but I want to record it on video. I hope the resolution is good enough. Yeah, that's about it. Thanks for watching. Bye.